Okay, hi guys. I'd like to just go through some of the ideas about how to get through the binary search tree lab. So how to get through, how to code all of these things. So we're basically going to be working our way through this PDF, and we'll just do a quick video just on how to get through all this code. So if we start off, we can open Qt Creator or our IDE or whatever we want to use. I'm going to say new project, and I want to go non-Qt and plain C++ project. Okay, I'll call it BST. Next, and that opens up a blank project for us, which we can see here. If I go into the .profile, we can see that it's using C++11, and that the file that it's going to compile is main.cpp. If we go into main.cpp, we can see it's given us a default hello world program. Now I'd given you some code already that was up on Moodle, so I'm just going to replace that in here like this and save. Alright, so if we look at some of the code here, the first thing that we can see is that we're implementing this in a very similar way to the way that we implemented a linked list. So when we had a linked list, we said that we had a class called link, something like this, and that our link class had an integer value and it had a link star to the next item. So what we're doing for our tree is we're saying we're doing the exact same thing. We've got some value stored over here, and then instead of just a pointer to the next item, we're going to have a pointer to a left child and to a right child. We initialize both of those as the null pointer when we start off, and in our constructor we see that the constructor takes in a value and it sets our integer value to that v that we give it. The destructor, we see that it's actually it's using a nifty little trick here, and what it does is it says in order to delete the current node, you first delete its left child, then you delete its right child, and then we're happy for the current node's memory to be released. If you call delete with null pointer, then it simply does nothing. Same thing for right if we call delete right and that's null. So if there's no child, then it simply does nothing and the current object gets deleted. If it does have a child, it first deletes that child and then allows it to delete the current item. So the benefit of that is that if we want to delete an entire tree, we can simply delete the root, and by deleting the root, that will then delete its item on the left, which will delete its item on the left, 24. 24 doesn't have any children, so it gets deleted and removed. Then we delete the right and the left, so it gets deleted. 35 gets deleted, 30 gets deleted. The left has been deleted, now the right gets deleted, so it deletes 61. Okay, but in order to do that, it first deletes the left, so it deletes 58, then 62, then 61. Now it's deleted 30, then 61, so it can now delete 50. And we'll see that that looks an awful lot like one of our traversals. So think about how that works, and see if you can figure out which of the three traversals that ends up doing when it's deleting an entire tree. Cool. So then, just like we had with our actual linked list, we had our link class. So in this case, we have the tree node class, and then we have the actual tree. All right. We have a pointer called root, which will point to our initial node, and then that in turn will point to the children. We set that to null pointer at the beginning, and in its if there's a default constructor, is there? No, there isn't. So when the tree gets constructed, it will simply set this item root equal to null pointer, and then it will carry on with whatever else it needs to do. Okay. So you see that I've given you an insert function. So the insert function takes in a pointer to a tree node, and that's a reference to a pointer, which means that if I change this pointer inside the function, it will change the original thing. So For example, if I was in some other random function and I said insert 42 and root, if root is null, then it says, is subtree null? Yes, it is. So then it updates subtree to point to some new item. Okay, so in this case 42. Okay, so it's important that we see, because we've passed a reference to a pointer, it means that we can actually update the original pointer that we had. And that's very important later on when we're trying to do a delete. We'll find that it saves us a lot of effort there. So we see if it's a null pointer, it simply inserts the item where we are. If the value is less than the current item's value, then we go left and we insert into the left-hand side. Otherwise, if it's not less than, which means that if it's greater than or equal to, then it recursively inserts into the right-hand side. So this is a recursive implementation of an insert function for a tree. You can also do this by simply having some cur pointer and traversing inside a loop until cur dot left or right is equal to null. But this is certainly the easier of the two implementations. Alright. We then see that there's a pre-order traversal function that takes in a pointer to the root. Okay, the root of whatever subtree we're at does the pre-order traversal. We're going to have to code that one, the in-order and the post-order traversal. We're going to have to code the min and max function. We're going to have to code the contains function and the remove function. Alright, so these ones are all, they all take in a pointer to a subtree. So they take in the root where we are at the moment, and then we're allowed to call them recursively if we want. If you'd like to build them iteratively, that's perfectly fine, but in this video I'm going to do most of them recursively. Just like with our code the other day, in order to call our recursive function, we often have another function that just kicks it off at the start. So I call min and I give it the root as the subtree. And then that way when we call myTree.min, okay, then we don't have to pass it the root by itself. This one will pass it in for us. Same with max, same with contain, same with remove. Alright. When the tree is being deleted, we see that we can simply delete the root node. And because of that nifty trick that we had up in our tree node class, we see that this will delete root, which will delete its left and right children first, which in turn will delete their children and their children and their children, and all the way down until all the nodes have been deleted. If we get to our main function, we see that it's declared a tree called t, some integer called value, and then it reads in a value, reads in a number into value, and then it checks that that value was not -1. Okay? So when we evaluate cin arrow value, what it will check is whether it was able to read in a value. If it was able to read something, that will be true, and then it will check whether value was -1 or not. If it was unable to read something, then it will be false and anything is false, so it doesn't even bother checking that, and the whole loop would finish. Okay. Now in the previous code that we've written, we saw something that was called an iStream, right? And we had a couple of functions that took in a reference to an iStream like this. And I said that there were times when we could pass in cin or we could pass in the fstream. Now in this video I'm going to show you something slightly different as well, and it's something called a string stream. And we can include that by going #include sstream, like that. And then down at the bottom, I can declare a string stream. And I'm going to call it ss. And in that constructor, I'm going to give it a string. Okay. Now, in this case, the input to our function, the input to our whole program, was that I was supposed to type in 50, 30, 35, 61, all of those things, all the way down. And then once that had all been input, then it would come in through cin, and we'd read it all in and construct the tree, right? So in this case, what I'm going to do is, rather than reading from cin, and rather than reading from a file, I'm still going to make use of the fact that this is an in-stream, and I'm going to construct it just using a string. So it's the number followed by a new line character, a number, new line, etc. Okay, this is not necessarily the best way to do it, but it's just that I want to show you guys how to use the string stream in this case. So now, rather than using cin, I'm going to go ss, and now this means that this works exactly the same way as it did before, but it will read up until a new line character, try and parse that as an integer, because that's what value is. So it will read this first bit, put 50 inside value, check it's not -1, call insert. Then it will read from there onwards, and it will insert 30, and then it will read from there, and insert 35, and 61, 24, 58, 62, 32. Alright, and so if our function is working correctly, that will construct this tree. And so if we just look through it, we start off with an empty tree, we insert the value, the number 50, so it goes in the root. After that, we insert the number 30, so we say, do we go left, do we go right? So 30 is less than 50, so we go left. So 30 goes over there. We then try and insert 35, so we go back to the root. We say, is it less than 50? Yes, so we go left. Is it less than 30? No, it's not, so we go right. We find an open space, and so we insert 35. We then insert 61, so it goes to the right of 50 because it's bigger than. We insert 24, which is less than 50, and less than 30. We then insert 58, which is greater than 50, so we go right. Less than 61, so we go left. We insert 62, which is greater than 50, greater than 61, and we find an open spot. 32, so it's less than 50, greater than 30, less than 35, and so it goes there. And then -1, at this point that will be false, and so the loop will finish and we won't end up inserting anything else. So if I go from here, I can now run it, and it seems to run without crashing. It doesn't seem to cause any problems. Alright. So we seem to have code that's reading in and constructing a tree correctly. So we can now go back to our PDF, which I've now lost. Here we go. So we're going to our PDF, and the first thing it says is write a C++ program that reads in from standard in, and it must construct the binary search tree, okay, which we've got already. Once it's constructed, it must do the pre-order, in-order, and post-order traversals. Alright, so we can see I gave you the pseudocode for doing the different traversals, and those were all fairly straightforward. It says, in order to do a pre-order traversal, you print out the value, you then traverse left, you then traverse right. Okay, so let's go to our pre-order traversal function. We see there's this one over here, and it calls pre-order traversal from the root, and after that it outputs a new line character. So we can now go to this version of the function, which takes in a pointer to a subtree. So that's this one over here, and we say the first thing we need to do is to print out the root. So subtree dot value. Right. After that, we need to traverse to the left, and so we said, if there is a left subtree, so if the left is not the null pointer, then do a pre-order traversal of the left. Following that, we say if the subtree dot right exists, then do a pre-order traversal from the right. Just like that. Okay. Now if we look at the output, it's supposed to output a number and then a space, and a number and a space and a number and a space and a number and a space. Okay. So what I'm going to say over here is when we output a number, I'm just going to output a space after it, just like that. Now what will happen is it will print out the value of the root followed by a space. Then it will go left, do the pre-order traversal on the left, print out a space after each number. So that does mean that we're going to end up with one extra space right at the very end. Now in this case I've set up Moodle that Moodle will still mark that correct, and that's not something you need to worry about for now. But if we really had to think about it carefully, I'm sure we'd be able to come up with a good way of how to solve this. So we now think that our pre-order traversal is working, so we save, we go down here, and we're going to do some stuff. So in this case, we're going to call our pre-order traversal, just like that. If I try and run the program, you can see it runs, and it's given us some numbers. So let's compare to what the PDF gives us. So this is 50 and 50, 30, 24, 35, 32, 61, 58, and 62. Alright, so it's given us the correct numbers there for our pre-order traversal. If we have a look at this, we see it prints out 50, then it goes left. Prints out 30, then it goes left. Prints out 24, tries to go left, it can't. Tries to go right, it can't. Goes back up to the parent. It's gone left, now it goes right. Prints out 35, goes left. Prints out 32, can't go left, can't go right, goes back to the parent. It's gone left, tries to go right, nothing left to do. So it goes up to the parent. It's gone left and right already, so goes up to the parent. It's already gone left, so now it goes right. So it prints out 61, then goes left, prints out 58, can't go left, can't go right, goes back to the parent, right? We've already gone left, so we go right, prints out 62, goes back, and we're done. Alright, so there is our pre-order traversal. Print out the value, go left, go right. Let's see if we can implement this for the other things. So from here, we now need to go and say, we can take the same code that we had before, and we can say, now we want to go left, then print out the value, and then go right. Okay, so it's the same idea as before, but we go left, value, right. And then when we do our traversal, we just need to be very careful that we call the correct version of the function. So we say, can we go left? Then we print out the so if we can, we go left. Then we print out the value. Then we say, can we go right? If we can, we do the traversal for the right. We should be able to do the exact same thing when doing the post-order traversal. And this time we go left, then right, then print out the value. And again, we need to be careful that we do the correct recursive traversals there. Okay, I'm sure in quite a few cases you might have copied it and then ended up having an in-order traversal inside the post-order one. So you just need to watch out for that when you're coding. And that should be our traversals. So if we go down here, we can say t.inOrder traversal, and then we can go t.post-order traversal, just like that. If we run the code, we can see there's our output. If we have a look at the tree again, so the in-order traversal says go left. Okay, so we go from here, we go left. We go left again, we go left, and we can't. So we print out the value, we go right, and we can't. So we go back up. We've gone left, so we print out the value, then we go right. So far we've got 24 and then 30. Now we go right. We're here, and we go left. So we print out 32, then we print out the value, 35, and then we go right. So we've got 32 and 35. We've gone right from here, so now we go back up to here. So we've gone left, now we print out the value, 50, then we go right. Now we're at 61, we go left. We're at 58, we go left, we can't. We print out the value, 58, we try go right, we can't. So we go back to the parent. We've now gone left, so we print out the value 61, and then we go right. We're now at 62, we can't go left, we print out the value, we can't go right. Okay, and that will give us our in-order traversal. And remember that the in-order traversal gives us all the numbers in order. Right, so that's looking correct. If we look at our post-order traversal, so the post-order traversal says go left, go right, and then print out the value. So we start at 50. We go left, so we're now at 30. We go left, we're now at 24. We go left, we can't. We go right, we can't. we print out the value, which is 24. We then go back to the parent. We've gone left, now we go right. So we go from 24, we're now at 35. We go left, we go down here, we're now at 32. We go left, we can't. We go right, we can't. Now we print out 32. So we've finished at 32, we go back up here. We've gone left, now we go right, we can't. Then we print out the value, so 35. We've done 24, we've done 35, so now we print out the value, 30. So we've now gone left from 50, so we go right. So we're at 61. We need to go left. So we see 58. We need to go left. We can't. We go right. We can't. We print out the value. We've gone left, so now we go right. We're at 62. We go left. We can't. We go right. We can't. We print out the value. So we get 62. We've gone left. We've gone right. So we're now done with 61. We print out the value and we go back up to its parent. We've gone left from 50. We've gone right from 50. So now we print out the value, 50. Okay. Make sure you get good at doing those by hand. If you can do them really quickly, those are a lot of free marks in your tests. All right. Cool. So if you compare those to the PDF, you'll see that those are the correct numbers, and we can move on to the next functions. Right. At this point, you would want to submit the code as is to Moodle for question 1, and we'd see that it would work for question 1. Right. The next step, submission 2. The program should build upon the previous one. The input is the same, and you must construct a binary search tree. You must find the minimum and maximum values and output them. Just like that. So we know that in order to get the minimum value, we just keep going left. We go left, 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 all the way until we can't go left anymore. Same if we want the maximum, we just keep going right. So I said we're going to focus on doing the recursive solution for this. So what we can also say is that if we have a tree like this, and I say what is the minimum value in the tree rooted at 50, we know that the minimum value in this tree is also the same thing as the minimum value in its left subtree, right? Because we know that the minimum value of the whole tree will be on the left-hand side of the root, just like we know that the maximum will be on the right-hand side. So the minimum value of the whole tree is the same as the minimum value of the left tree. Okay? So we can simply say that if there is a left tree, then it's the minimum value of that tree. And we can simply keep recursing until we get to 24, until we get to the left-hand side, and we say, what is the minimum of this tree? Well, there is no left-hand tree, which means that the root, the subtree where we are at the moment, must then be the minimum in the entire tree. So we can say, if there is a left subtree, then we can simply return the minimum of that subtree. If there isn't a left subtree, then we know that the minimum of the entire tree is just whatever the value is where we are at the moment. So in that case, subtree.value. Now there's one thing that we would need to think about over here, is that over here I'm dereferencing subtree. Okay, I'm going subtree, follow the pointer, and look up left. So I'm dereferencing subtree, but I'm not checking whether it's the null pointer. So if you passed the null pointer into this function, then we would get a segfault when we're trying to dereference it. And that would be the same for all of these recursive functions over here. Ideally, you would need to check whether subtree is null before you do any dereferences. All right. So I guarantee that in the tests that we're running, I'm never going to try and do that. So I'm never going to ask for the minimum value of an empty tree. And so in that case, you're guaranteed that subtree won't be null. All right. So we can do that in order to find the minimum value, in order to find the maximum value. It's the exact same thing, except we want to go right every time. Right. So we say that if there is a right-hand tree, then we know that the maximum of the entire tree will be the same thing as the maximum on the right. Right? So the maximum of this entire tree is the same as the maximum of the tree that's rooted at 61, which is the same as the maximum of the tree that's rooted at 62. Okay, so that's the exact same thing over here. If we go down, so maybe let's comment those out so that we've still got a submission, and then we can say cout t.min, oops, cout t.max, just like that. And if I run the code, we see that it gives us 24 and 62, which we see are indeed our minimum and maximum numbers. If we look at the PDF again, we can see 24 and 62 are what we expected. Cool. So submission 2, that should work. Submission 3. Okay, this question says, the input is all in the same format, build on all the previous stuff, blah, blah, blah. Read a number from standard in, print out true or false, depending on whether the number is in the tree or not. When it reads a -1 a second time, then it must finish. Okay, so in this case I am then going to say let's read from cin for this last section. So what I'm then going to say is let's take this loop again, just like it was, but let's do it with cin. And then we can simply say if t.contains the number that we've just read in, then we can cout true, else cout false. Just like that. Now, if our .contains function works, then this should work for us as well. So let's have a look at the contains function. So contains over here returns a Boolean value and takes in an integer, and it asks the question, does the tree rooted at root contain this value? So if we go off to that function, we can see over here, and we can look at our tree. We can say, if we start off at here, and we want to know, does this contain the value 42? So what do? We say, is the current node equal to 42? Yes, it is. We return yes. No, it's not. We say, do we go left or do we go right? So we're looking for 42, so we go left. Is this equal to 42? No, it's not. Do we go left or right? We go right. We see 35. Is this equal to 42? No, it's not. 42 is bigger than this, so we go right. We see that we can't go right anymore, and so in that case we can return false. So we said the first thing we need to do is check the value of where we are at the moment. Right? So we can say if subtree.value is equal to the item we're looking for, then we can return true straight away. Okay, at that point we know we've definitely found the value and we can simply return, we don't need to do anything else. After that, we can say if it's not equal to the value we're looking for, then we say do we go left or do we go right? So we can say if value is less than whatever's where we currently are, then we return a recursive call. And we look for the exact same value, but this time we're looking in the left-hand tree. Just like that. So if the value is less than the current one, we go left. And if the tree contains it, then we simply say, does this subtree contain it? If the subtree does contain it, we know it's in the tree. If the subtree doesn't contain it, we know it's not in the tree, because we're guaranteed it couldn't possibly be in the right-hand side one. After that, we can simply say, well, if we know that it's not on the left, or we know that it's not supposed to be on the left, we know that it's supposed to be on the right, then we can do the exact same thing, except we search to the right. Right, and that will check whether it contains. Now, at this point, we're going to have one problem, is that we never check for null. So I could get all the way down, say down to here, say we're looking for number 25. I then say, okay, well, we would end up searching to the right. Okay, because 25 is not equal to 24. It's not less than 24. So we would go in here. we would then call this function of value and null. When we go into that recursive call, we would go null.value, and we would get a segfault. So in this case, we need to do one of two things. Either we need to check before we do a recursive call and make sure that we can actually go left. So we could say over here, for example, if we're supposed to go left and the subtree on the left is not null, then we know we're okay. And in this case, we would then also have to check over here and say that value is now greater than or equal to subtree.value, and we're allowed to go to the right. Right, not equal to null pointer, just like that. Now at this point, we've now introduced a case where you could say this is false, this is false, this is false, and so it never goes into any of them. And so we would have a problem where the function can finish without ever returning something. We see if we compile, we can see control reaches the end of a non-void function. Okay, so that's a warning from the compiler. And so in this case, we should be suspicious of warnings. So we have a look and we see, okay, well, yes, we could potentially reach the end of this function. So in that case, we would need to say else return false. Because we know that if it's gotten here, it means that both of these were false, which means that either we had to go right and we couldn't, or we had to go left and we couldn't. Okay, so in that case, we know that we haven't found it. So this is one way to do it. The other way, which is quite a bit easier, is to rather check at the end. So we go back to where we were earlier. So we say just like this. And we simply say, right before we do our first dereference, we can say if subtree is null. In that case, we've gone off the edge of the tree. We've gone left because we were supposed to go left, but it turned out that there was no tree there, and so there was nothing we could do. So does the empty tree contain the number 42? Well, no, it doesn't, because it doesn't contain anything. So we could simply say, in that case, just return false straight off the bat. Just like that. So if I run the program, we can see it's read in our tree and it's waiting for input. So if I go 50, it will say, yes, it does exist. If I say 30, yes, it does. 24, yes, it does. 32, yes. 35, yes. 61, yes. 58, yes. 62, yes. All those things exist. If I ask for 42, no. Okay, because it doesn't exist. If we go 1, no. 51, no. 62, yes. 63, no. Alright, so it seems to be working fine. If I go -1, we can see at that point the program finishes. Okay, so at this point we should be able to pass submission number 3, and so you can submit that code as well now. So we could go there, and let's put it down there so everything's in order. Okay, so that was submission number 3. Then finally we have submission number 4. Now submission number 4 was the tricky one. So the program said do all the same stuff as before, construct the tree, all of that. Then it says read a number from standard in, find the number in the tree and delete it. After that, perform the traversals from earlier. Continue doing that until we read a -1. Okay, it says use the same algorithm covered in class, and this site over here, if you click on that link, it will take you to a website that tells you the same stuff as what we did in class. Basically, our algorithm from class said that if it has no children, you can just delete it, okay, and set its parent to point to null. If it has one child, then you can say set its grandparent to point to its child instead. So if we were deleting 35, then 30 would point to 32. If it has 2 children, then we take one step to the right and we go as far left as we can. So if we're deleting 30, we go one step to the right and as far left as we can, so we get to 32. We then move 32 up there, and then we delete 32 from this right-hand subtree. Okay, and so we can see that that gives us a fairly straightforward recursive algorithm for this. Excuse me. So we can go back to our loop over here. We can say read from cin, from cin. Then we say t dot remove and remove the value that we just entered. Simple as that. So we go to that function and we see that it takes in a value, calls the recursive function, which takes a value and a root. Alright, now if we go to that one, we see that it takes in the value, it takes in a pointer to a root, and that pointer is a reference, which means that we can update it if necessary. We can update the original one by changing subtree. Cool. So the first step is to traverse to the correct place. So we need to be able to say, are we at the correct place? If we are, then do the removal. If we're not at the correct place, well, then we need to keep traversing. Or we could potentially say, well, we can guarantee that we can't find it. So let's first handle the case when we know we can't find it. That's the exact same thing as that we did up here. So let's take that and there, and we can say if subtree is null, it means that there's no possible chance of finding value in this tree because there's nothing left in it. And so at that point, we can simply return. We can say there's nothing left for the function to do, it can just exit. Happy. Following that, we need to check 3 different cases. We need to say, have we found it? Okay, so it's these 3 cases as well. So we can say, have we found it? So in fact, I'm actually just going to copy this. I'll say there. And we can say, we found it. And now we can delete. Right? And we don't need to worry about a return. Otherwise, we say, well, the value should be in the left subtree. So let's call delete or remove of the exact same value, and we're deleting it from the left-hand side. Then likewise, if it's not supposed to be on the left, then it's supposed to be on the right. So we delete the exact same value, and we're deleting it from the right-hand side tree. Okay. So we now only need to look at this last case. See, this is the really nice thing about recursion, is that we simply say, as far as I'm concerned, if I'm deleting the value 32 from this tree, it's the same thing as deleting 32 from this tree, which is the same thing as deleting it from this tree, which is the same thing as deleting it from this tree. And that's the nice thing about all this recursion. Okay. So if we've now found the item, we need to consider the different cases. So this is a binary tree, so we know that it can have 0 children, 1 child, or 2 children. So let's handle the easy case first. Okay, if it has no children. So if subtree dot left is equal to the null pointer and subtree dot right is equal to the null pointer. So in that case, we know that there are no children left. It's just like deleting 32 from here. Okay. And so in this case, we just need to say, well, what do we actually need to do? So in this case, we need to delete the node where we currently are. Okay. And we need to set the pointer that's pointing to it equal to null. So we need to set the left-hand pointer of the parent equal to null. Now in this case, we can do that because we got here by calling subtree.left of its parent. Okay, and because it was passed by reference, it means that whenever we update subtree, we're updating the original one that we had. So it would be updating its parent's left function. So if I do something like this, I could say delete subtree. So that says follow the pointer subtree to the thing that it's pointing at. So we're pointing at 32 and delete that object, right? Once that object is deleted, we set this reference pointer. So we set the parent's pointer equal to null. Alright, and that will delete the object. After that, we then need to say, well, what if there is one child? Okay, so if we're looking at our tree, what happens if we're trying to delete the number 35? Alright, so there's one child. So let's go here, else if, and let's see. We're going to say, what if the left child, there is a left child, and there isn't a right child? Okay. Well, in that case, I want to say that the parent, so 30, should point to my child. Okay. So in this case, I'm going to say the parent pointer, which in this case we know is subtree because it's a reference, right? It's a reference to the parent's pointer. So if we update subtree and make it point at something else, it means that we're updating the parent to point to something else. So rather than pointing 30 to 35, 30 will point to 32. So we can say subtree equals subtree.left. Easy as that. Now there's just one catch, is that we still need to delete the node for 35. Okay? But we can't just say delete subtree like we did before, because this would then recursively delete its child. So if I just call delete 35, it will then delete 32 because it deletes its left child first. So we're going to go tree node star, and we're going to create a temporary pointer that will point to this left-hand child. That way we don't lose it. Then we can say subtree.left is equal to the null pointer, which means that the current node, 35, its left child is null. Okay, so 35 no longer points to 32. At that point we can delete it, and we can delete it safely, and 32 doesn't disappear. And then instead of that, we now say that is equal to temp. Just like that. Easy. From there, we can now say, well, we can handle the case when there's one child on the left. Well, what about the case when there's one child on the right? Well, it's going to be exactly the same, except we're going to do it on the right instead of on the left. Okay? And we're going to say, rather than remembering where the left child is, we're going to remember where the right child is. We're then going to set the right child to null. We're going to delete the item that we were trying to get rid of. And we then set the parent to point to temp. Cool. So hopefully we can now sort out, hopefully this now covers the cases where there is only one child. We can handle the left-hand side case, we can handle the right-hand side case, and because we've been careful about keeping temporary pointers, we know that we haven't deleted 35 and that hasn't in turn deleted its child. Okay, so that was the one trick that we just needed to be careful of about doing this up here. Okay. So finally, if there isn't no children, there isn't one left child, there isn't one right child, that must mean that there are two children. And we know that that is the only case that's left. Okay, so there were only 4 cases in total. Okay, well, 3 cases, there were 0, 1, or 2 children, and the one child could be on the left or the right. So now we're saying if there are 2 children, okay, and so our algorithm says find the minimum value in the right-hand subtree. Okay, update the current item's value with that minimum value, and then remove that value from the right-hand subtree. Okay, so what I'm going to say is take the current node, set its value equal to the minimum value in the right-hand subtree. Just like that. Now that I've got that done, then I need to say delete that value from the right-hand subtree. And this is where recursion is incredible, because at this point we can simply say, well, we already have a function that can do that. It's called remove. Okay, it's the function we're actually busy with at the moment. So we can say remove that same minimum value, which we've just stored over here. We've just stored it in value. And we're going to say remove that value from subtree.write. And that will now delete that value. And we know that our function can handle this case because the minimum value in the right-hand subtree can only possibly be one of these cases up here. The minimum value on the right, okay, when we get to that thing over here, 32 in this case, we say either it can be a leaf where it has no children, and our function can handle that already. So we're quite happy that that will work. Okay. Or it can have one child, and that child would have to be on the right-hand side. It would have to be bigger than 32. Okay. And we know that it has to be on the right because if it were on the left, then when we were searching for the minimum, well, we would have gone left one more time. All right. And so we would be sure that we can't go left again from there. So it would either be there are no children, or the left is null and the right is not. And in both those cases, we know that we can successfully delete the item. Okay. So with any luck, that should do everything. So if I try and compile, okay, it builds correctly. We can see there were no errors there when it built. If I go back down, we see this was all fine. The only thing we haven't done is print out all our traversals again. So I'm going to say inside here, we're going to print out a traversal every time we remove an item. So if I go run, it's now waiting for us to enter in an item. So let's open up our, so I'm looking for the PDF here. So we're back on the PDF. We've already inputted all of those. So now we want to say, try and delete the value 30. Okay, so that's actually starting off by doing the hard one. So that's saying, can we delete something with 2 children? So let's take a step back and say, well, can we delete something with no children? So let's try delete the value 24. So I'm going to hit 24, enter. Okay, so first good sign, we see the 24 is no longer part of the traversal. Okay, so that's a good thing. Okay, 24 is gone. But let's double check ourselves. What should the traversal be if 24 wasn't there? Okay, well, it would simply be, if we do the pre-order traversal, it says print out the value, then go left, then go right. So print out the value. So 50, 30, go left. Well, we can't because 24 is no longer there. So we've printed 30, we can't go left, then we go right. Print out the value, 35. Go left, 32. Print out the value because we can't go left or right. Then we're back there, we're back there. We've already printed out 50, we've gone left, now we go right. So we're over here, pre-order, so now we print out 61, we go left. We print out 58, we go left, we can't, we go right, we can't. Back to the parent, we've gone left, we go right. 62, print out the value, can't go left, can't go right, backtrack, backtrack. And we're done. So we see 50, 30, 35, 32, 61, 58, 62. And so that's the correct pre-order traversal. Same thing if we do our in order, we see it would be 30, 32, 35, 50, 58, 61, 62. And so that's also correct. And if we do the post-order traversal, it should be go left, go right, print out the value. So go left, we're over here. Go left, nothing to do. Go right, we're over here. Go left, 32. Go right, nothing. 35. We've gone left, we've gone right, print out 30. We've gone left, now we go right. So we're at 61, we go left. We see 58, print out the value. Then we go right. 62, print out the value. Now we've gone left, we've gone right, print out the value, 61. Okay, now we're back up at 50. We've already gone left, we've already gone right, so we print out the value, 50. Right, so we see that our code seems to be working. Maybe we can try a few more. If I delete 58, right, we see that 58 has disappeared. If I go 62, Okay, that one seems to disappear fine. If I now I've deleted 58 and 62. Now I can delete 61. And we see that all seems to be working fine. Cool. So we can successfully delete things that have no children. Let's see what happens if it's something that does have a child. So let's try and delete 35. Okay, well, it looks like 35 has successfully disappeared from our list of numbers. Let's do the traversal. So it would be the pre-order traversal says, print out the number, go left, go right. So we expect to go 50, 30, 24, then we go right, but we've deleted 35, so we would get 32 because 32 is now up here. So it should be 50, 30, 24, 32. Now we've gone left, we go right, we're over here, 61, 58, 62. And we see that that is correct. Gives us the right number. Alright. Okay, so we now try the interesting one. Stop, let's run it again. Now let's delete something with 2 children. So I'm going to delete, let's delete 61 first. So if I delete 61, we expect to go one step to the right and all as far as left as possible. So we get 62 moving up there and 62 over here being deleted. Okay, so we go 50, 30, 24, 35, 32, 62 because that's moved up now, and 58. So that's worked correctly. How about deleting 30? Okay, so 32 should now have gone up there, and then 32 would be deleted from here. So we expect to go 50, 32, 24, 35. Then we deleted 61, so 62 is moved up, so 62 and 58. So our pre-order traversal there looks correct as well. How about now if I try delete 50, so I delete the root. Okay, well, we expect to go one step to the right and as far left as possible, so we expect 58 to now be the root. So we would expect, maybe let me go end this one, maybe let me run it again from scratch, just so that we're back to the original tree. If I go 50. Okay, so now 58 has moved up to the root instead of 50. And so our pre-order traversal goes 58, 30, 24, 35, 32, 61. There's no 58 because it got moved up earlier, and 62. Alright, so there we have it. Our recursive version of remove seems to work in all of the different cases. Alright. Now, there is one or two things that we could do to clean this up if we really wanted to. We could do, maybe we can see in every case we're calling subtree we're calling delete subtree, and we're creating this extra temp variable. So we maybe could factor some of that out. But maybe I think it's fine. I think maybe we can leave it at here. Alright, so I hope this gets you all the way through that that lab on binary search trees. If you have any questions, post on the forum or feel free to email me. This is definitely the stuff you want to know how to do, because your second lab test, if it happens, would be on this kind of stuff. Alright. Cool. I hope this helped. Have a good evening.